Hi, my name is Chris Britton, and I'm a PhD candidate in the Edge Lab. Over the next few minutes, I will give you an overview of one of the research projects in our lab, MOOC Performance Prediction via clickstream data and social learning networks. Massive Open Online Courses, or MOOCs, have grown drastically in popularity over the past several years. Platforms like Coursera, edX, and Udacity offer courses that have tens and even hundreds of thousands of students, offering them a variety of learning modes by which they can learn the material, including video lectures, in-video quizzes, and discussion forums. But these courses often only have one or two instructors, and as a result, the teacher-to-student ratios are extremely small. For this reason, and many others, these courses exhibit high drop-off rates in participation and completion over time. The question we want to ask is, how can we increase efficacy of instruction and engagement of learners in massively scaled courses? We are approaching this problem through two paths, each of which uses the fact that a plethora of information is collected about students as they interact with the learning modes on MOOC platforms. One is the development of detailed analytics about student learning that can be shown to an instructor through a dashboard interface, allowing him or her to gain keen insights into the learning process and in turn use that information to determine where his or her assistance would be most beneficial. The other is the development of techniques for automated content individualization. In this video, we will focus on the former and direct you to our other video on individualized learning for the latter. Ideally, an instructor dashboard would have a number of useful features built into it. These include recommendation, for example of study buddies, visualization, for example of the learning network of interaction, and prediction, such as the drop-off rate over time or performance on future assessments. Prediction itself has implications to other modules because the methods used to model student performance can also be useful in recommendation and visualization. So prediction will be our focus in this video. There are two initial research questions we have investigated in this project. The first is it possible to correlate student performance on assessments with their video watching behavior? This would be the first step in relating behavioral measurements to learning outcomes, and is enabled by the fact that these platforms collect a lot of information about each student. As an example of this, we would like to know, does pausing more in a video indicate whether a student would tend to understand that material more or less? And is there even such an association to begin with? After answering this question, the second is, can we in turn use student behavior to predict their performance better than we can without it? In investigating these research questions, we have used data from one of our own MOOC courses. To investigate Q1, the first step was to determine quantities of interest for each user video pair. One is whether the user was correct on first attempt, or CFA, at answering the question or not. The other consists of 9 video watching quantities that are computed from the clickstream data and that we identify as potentially relevant to performance. Fraction of time spent playing the video, number of pauses made, number of rewinds made, average playback rate, and others. Then, by aggregating the data together over all users in all videos, we compute the probability distributions of each quantity in each class, CFA and non-CFA, to see if there were any qualitative differences between them. We were able to extract certain intervals of values that showed a difference between the behavior of CFA and non-CFA instances for most of the 9 quantities. For example, with fraction completed, values of below 0.15, which indicates that the student had watched less than 15% of the video, indicates that a user was more likely to be incorrect on the question for the video, and values above 0.75, meaning that they watched more than 3/4 of the video, indicates that the user was more likely to be correct. We used a 2-sample test for proportions within these different intervals to verify that there was a significant difference between the classes. From this analysis, some of the qualitative characteristics we identified that indicated a higher chance of being CFA than not were, for example, having completed more than 3/4 of a video, having paused more than once, having changed the playback rate at all, and having rewinded at least once. The purpose of the second research question was to use the knowledge we had gained about the correlations between video watching and performance to design a prediction algorithm. The idea was to generalize the procedure of interval extraction and success estimation that we just saw, so that it can be used to make a prediction on the score that the user was likely to get on the question. We tried a number of different algorithms and variations from machine learning. The procedure that we found worked the best can roughly be described as follows. For each clickstream quantity, we first use kernel density estimation, or KDE, for each class, which serves as a way of estimating the probability density functions. Then, we compute the intersection points between the classes, and the spaces in between these points become the intervals. Finally, we compute the empirical success estimates within each interval by comparing the amount of density in the CFA and non-CFA classes for that specific interval. With the success estimates in hand, we build a support vector machine, or SVM, classifier over the training data. The features used in the design matrix, X, are indicators of the specific user and specific quiz, as well as success estimates of the features, as shown here. The target vector, Y, is composed of zeros and ones, with a 0 when the answer was incorrect and a 1 when it was correct. The learned parameters of the SVM classifier then serve as a model for the probability that a user on a given video will answer the question correctly. In evaluating our prediction algorithm, we compared it to a number of standard algorithms that have been applied to educational datasets in the past. The standards that we used are k-nearest neighbor, or KNN, biases, which includes a separate bias term for each student in each quiz that is learned through machine learning algorithm, and matrix factorization, or MF, which adds product or interaction terms between the specific users and quizzes on top of the biases. We evaluate two different variants of our algorithm, VID-N, which is the standard implementation we described before, and VID-A, which applies an adjustment within each of the quantity intervals to account for varying sample sizes. These algorithms, both the standards and our design ones, went through an extensive tuning procedure to set the specific parameters in each case. This chart shows the results that we obtained. We compared three different metrics: accuracy, root mean squared error, or RMSE, and AUC, which accounts for the trade-off between the true and the false positive rates. We plot these as a percent improvement relative to a naive prediction scheme, which just serves as a benchmark. We also compare the quality of these algorithms over different dataset partitions of interest: active users over the full course, all users over the first 2 weeks, and all users over the full course, which is the full dataset. The key observation from these plots are as follows. First, our algorithms do show improved performance relative to the standards in all cases for all metrics. Second, the improvement in our scheme is particularly pronounced early in the course, before it is clear exactly who the active users are. The reason for this high differential in this case is that there are relatively few entries for each individual user, which puts the biases and MF algorithms at a clear disadvantage since they rely on explicit user performance data. As a result, we see that these standards are much more sensitive to per user and per quiz information, so that clickstream data can be particularly helpful early in the course. We identify a number of next steps that we are currently investigating. First is to look at sequences of clickstream events and time series rather than just aggregate quantities. This could presumably yield more information about patterns in user behavior, which may be used to separate between the positive and negative instances with higher quality. Second are a number of social learning network, or SLN, graph applications that are made possible by higher quality performance prediction. These include clustering students by their performance, user and quiz detection, which means identifying students who are particularly high or low performers, and quizzes which may be particularly easy or hard, and study buddy grouping, by pairing up students who have complementary sets of performance skills. Third is to incorporate other forms of behavioral data besides just video watching behavior. For example, MOOCs also have discussion forums, and other online course platforms, such as our MISC individualization platform that is described in another video, have other modules of learning like text and shared notes as well. Finally is to build out these algorithms in an analytics dashboard that can be deployed for MOOC and Flipped Classroom, or FLIP, where they can be subject to the real test, how useful these different measures are to instructors of these courses in staging intervention techniques to help students better understand the material. Thank you for your attention. If you have any questions, please feel free to contact me at cbrinton@princeton.edu.